So as Vishal said, I'm Jess Archer. I'm an engineering manager at Laravel. I'm also the head of Nightwatch. For those of you that don't know what Nightwatch is an observability application performance monitoring and observability tool, first party, specifically designed for Laravel applications. So it tracks errors, exceptions. Sorry, I want another slide over here. Here we go. So it'll track the errors that occur in your application. It'll track the performance of your application. It measures all sorts of events from your application and also collects the logs. Now, we launched Laravel Nightwatch back in June last year. And since the time of launch, we have ingested over 257 billion events from your Laravel applications. And each of those events is effectively a database row that gets inserted into our databases. Now, we don't hold on to the data forever, but right now, we have an individual table, our queries table in the US region. A single table currently has 35 billion rows in it right now. That is 18.5 terabytes of uncompressed data, or 705 gigabytes when it's compressed. Now, you might be wondering, how do we ingest all of this data from all of your applications into Nightwatch's databases? So this is what the architecture looks like. On the left, we have your application. So we have your Laravel app that's emitting all of these events. So database queries, outgoing requests, exceptions, all of this information. This all gets bundled up and sent to the Nightwatch agent, which also runs locally in your infrastructure to keep your application fast. The Nightwatch agent bundles up this data, and then it sends it off to our infrastructure, starting with our ingest endpoint. This is responsible for validating that the data is correct, checking things like your quota, and then it divides the data up into all of the different categories, and it puts that onto Kafka. So Kafka is an event streaming platform. It's fantastic for throwing messages on that can be consumed later by multiple systems. So from Kafka, the data is ingested by a service called ClickPipes. This is a managed service offered by our database vendor ClickHouse, and effectively it reads from these Kafka streams all these different topics, and it converts that data into insert statements, which are inserted directly into our database, our analytical database called ClickHouse. Now, this talk is mostly going to be about how we use ClickHouse, and so you might be wondering, well, what is ClickHouse? So ClickHouse is an analytical database. The acronym OLAP stands for Online Analytical Processing. This is different from the normal databases that we use in our applications, which are transactional databases, or OLTP. So ClickHouse is an entirely different style of database specifically designed for analyzing data. It's used by a lot of big companies such as Cloudflare, eBay, Lyft, Vimeo, and Microsoft. And in the case of Cloudflare, at last report, they were ingesting over 11 million rows per second into their ClickHouse databases. But why do I love ClickHouse? Well, it's free and open source, just like Laravel. Currently has about 45,000 stars on GitHub. And also like Laravel, it has excellent documentation and also an excellent community. And we also found that it was faster and cheaper to run than all of the competitors that we assessed. So now you're wondering, how fast is ClickHouse? So I'd like to do some demonstrations with some live queries that will be running on my laptop just to kind of give you an idea of what it can do. Now, to start with, I have loaded a data set into a few different databases so that we can compare them. So I have a data set loaded into MySQL, and we're just going to run this describe requests command and just see the structure of the table. So this is a very simplified version of our requests table where we store information about every request that comes into your application. So we have the timestamp column, the URL that was accessed, the HTTP status code, and the duration of the request in milliseconds. We store it in microseconds in Nightwatch, but for this example, milliseconds is a little bit easier. So now let's have a look at the indexes we have set up on MySQL, just so that you can see that we're giving MySQL the best chance at running these types of queries. So we only have two indexes on this table. One is an index on the timestamp column, so we can quickly look up data by timestamp, and we have a compound index on the timestamp column and the duration column. Now let's have a look how much data is in this table so that we know what we're asking of the database. So we're going to, first let's have a look at the shape of the data. We'll just have a look at some example rows. So we'll select the first 100 rows. And we can see they have timestamps, URLs, status codes, and durations. And this query only took 2.3 milliseconds to run. So how much data was that querying? Now we'll select the count from this table. And this takes a little bit of time to run, because there is actually quite a lot of data in this table. There's 20 million rows that we're asking MySQL to count. So that took 3.2 seconds. I have this data loaded into Postgres as well, also running on my laptop, and we'll ask it to do the same count. It's much faster, the same 20 million rows in about 580 milliseconds. Now let's ask ClickHouse to count this data. 4.1 milliseconds to count the same 20 million rows. Now, it'll get way better, trust me. So ClickHouse returns a bit of extra information. It tells us how many rows that it read and the size of data that it read. So we can actually see ClickHouse cheated here. It only read one row to do this count. So it's storing an internal counter somewhere. So it didn't really do any work. So we don't give it any credit for this yet. So we can modify this query, and we'll include a timestamp that is 1 second into our data set, which means that it can't just use that little internal counter it's got. It's actually got to do a little bit of work. 2.9 milliseconds, though, to count most of the records in here. And we can see it only read 8,193 rows to do this. So it's still cheating. It just read the first part of that data to figure out what to exclude from that 20 million. So ClickHouse is pretty clever at doing some of these tricks. But this is not a very interesting query. So let's do some more analytical heavy queries. So now we're back to MySQL. And this is the type of query we might run in Nightwatch to display information in a chart. So we want to show from our request data grouped by day, so one data point per day. We want to see the total number of requests, the count of requests. We want to see the fastest request, the slowest request, and the average request time. From our request table, grouping by the date and ordering by the date. So I'll run this query. I probably should have run this before I started talking on this, because this takes about 14 seconds, depending on if my laptop is plugged into power or not. Okay, it's running pretty good. I think I put it into higher power mode. So 7.9 seconds to query 20 million rows, which in some systems is not a lot. In some systems it is a lot. So these tools are designed for specific purposes, which we'll talk about. So we can see the data here, and I'll just kind of scroll through it just so you can see an example. So we have one row per day with the number of requests each day, the fastest, the slowest, and the average. This is an aggregate query, so it's had to read every single row in the database to do this work. We'll ask Postgres to run the same query, and it should be pretty quick, 1 second to do the exact same query. But if we're loading this on a dashboard, when someone just goes into the dashboard and we've got a lot of these charts, that 1 second is still way too slow. So now let's ask ClickHouse to do the same query on those same 20 million rows. And it took only 82.6 milliseconds to aggregate this 20 million rows. Thank you, ClickHouse. And we can see it read 20 million rows, and it read 160 meg into memory. Let's do one more for ClickHouse just to get warmed up on reading these database queries. So this time we want a URL report. So we want to get all the distinct URLs in this data set and find out how many requests have gone to each and their fastest, slowest, and average. So we're going to group by the URL instead of grouping by the date. Again, this runs super fast, 100 milliseconds, and if I press back and run it again, it runs even faster once the cache warms up. So you might be wondering, well, how is ClickHouse so fast, and what is the catch? So it comes down to how the data is stored on disk. In a row-orientated database, such as MySQL or Postgres, which are typically transactional databases, the data for each row lives together. So you've got row 1's data living together, then row 2, row 3, row 4, and so on. In analytical databases, the data tends to be stored in columns instead. So all the timestamps live together, then all the URLs, then all the statuses, and then all of the durations. To put this another way, if we imagine that our MySQL database was a CSV style file on disk, all of the data just lives together like this, and we can see row 1, then row 2, then row 3 in this linear fashion. Now, MySQL is fantastic at working on individual rows. So if we want to select one row from the database, all that data lives together. The index can help MySQL scan to exactly where it needs to in there and grab that row data out. But when we want to aggregate over a lot of rows, now we start to having to skip over all this relevant data, grab something, keep skipping over more irrelevant data. And this is what slows MySQL down. So its strength in being a transactional database becomes its weakness as being an analytical database. If we compare this with a column-orientated database like ClickHouse, every column is a separate file on disk. So all of the rows for the timestamp live in that one file side by side. We have our URLs, status codes, and our durations in separate files. So when we want to aggregate on something like our duration, all of that data just lives side by side. We can grab it very quickly and easily. But on the flip side, if we want to pull out a row of data in ClickHouse, it now has to go into all 4 of these different files and grab that data. So ClickHouse is not a silver bullet that will fix everything. It's a tool that's fit for a specific purpose. And in Nightwatch, we use Postgres and MySQL for different purposes. So all of our event data goes into ClickHouse, but our application data, such as user accounts and the applications and environments, those all live in Postgres. So how is data inserted into ClickHouse? Because it's ingesting all of this data very, very quickly. It needs to be able to get this data into your system very, very quickly. So every single insert statement you run in ClickHouse creates a separate, what's called a part, which is effectively a directory on disk. So a separate folder with all of the columns with just the data from that one insert. So ClickHouse really likes when you batch up your data and insert 10,000 rows or 100,000 rows at once rather than inserting one row at a time. Now, these parts are immutable. So every time we insert more data, update data, we don't edit that existing data because that would be slow to edit and pull apart those files. And so with all of these folders getting created on every insert, these parts or folders get merged in the background and go into larger and larger files. But this all happens in the background transparently to us. So it can ingest data very, very quickly and quickly join that together in the background without impacting performance. And how is the data indexed in ClickHouse? This is another thing that makes ClickHouse really fast. So in ClickHouse, you have a single primary key, and this defines the order that data is stored on disk. And this is one of the most important things with ClickHouse. The primary index is also sparse. So the index doesn't track every single value that is being indexed. It only tracks every 8,192nd row by default. And so when it needs to find data, it looks at the index, but then it has to read those 8,192 rows to find that data. So most queries, if you were looking for one row in ClickHouse, it's going to read a minimum of 8,192 rows. When we're aggregating, this is fine. And ClickHouse is fast at retrieving individual rows in the order of milliseconds, but MySQL will often do it in microseconds. There are other indexes you can use in ClickHouse, such as data skipping indexes using Bloom filters and all sorts of fun technology. And you can also use projections as other ways to optimize for different queries. But your primary key should be designed to support your most common query patterns. So what happens if ClickHouse isn't fast enough? So I have another table here called requests XL. So let's count how many rows are in this table. Still quick to count, but we can see we now have 1 billion rows loaded into my laptop in this separate table. So now let's run that same chart query on this 1 billion rows. And we'll see it took 1.3 seconds. So it's still very, very fast. This is a billion rows rather than the 20 million that we had earlier. But over a second is just not fast enough for the types of queries we need to run. So how can we make this faster when we get to this even bigger scale? One thing also to point out is that even though we have a billion rows in here, ClickHouse is still very fast if we filter that data down. So I've added here a where timestamp, and we've just chosen an hour's worth of the data. This table is ordered by timestamp, so we can run this query, and even though it's a billion rows, this query runs in 20 milliseconds because the index has helped it scan down to just that 1 hour's worth of data. So having large tables is not a problem. It's more if you need to read a large amount of data that becomes the problem. So let's look at the structure of this table so that we can look at how we can make this even faster. So this is our requests XL table. We have our timestamp column. The syntax here is a little bit different from MySQL, but pretty kind of similar. So we have our timestamp column that's a date time, the URL, which is a string, the HTTP status code, which is an unsigned 16-bit integer, and the duration as an unsigned 32-bit integer. The engine here is the merge tree engine. This is the base engine in ClickHouse that all other engines expand upon, and the merge tree engine is named after that merging process where all of those parts get merged together. This engine is perfect for all of the raw data that's coming into your system. And then in this case, we've defined our primary key as the timestamp, so the data will always be ordered by timestamp, which is really good when we want to filter by that timestamp, which in Nightwatch is the most common thing we're doing. We're looking at the last hour's worth of data or the last 7 days, so we're normally doing filtering by timestamp. So we can make this faster by creating an aggregate table where the data is pre-aggregated ahead of time, so we can query the aggregate table instead. So here we're creating a table called requests XL by minute. So we're going to aggregate the data by minute. So instead of our timestamp column, we have a bucket column. It's still a date time, but it's going to capture the minute that we are aggregating for. We then have our requests column that counts how many requests are in this bucket. We're using a sum here, which is similar to MySQL sum, but we have to tell this aggregate table that this column is going to store aggregated data. A sum is a simple aggregate. It doesn't need to maintain a lot of state. It just keeps adding values to it, so it's a simple aggregate function. The fastest uses the min, also a simple aggregate function, and then the slowest uses the max. The average is not such a simple aggregate because it needs to carry a little bit of state in order to, if you wanted to have, you have buckets by minute and you want to get the average over 2 minutes, it needs to be able to combine those averages together. So there needs to be a little bit of extra state so that it can pull those apart and join them together. The engine here is the aggregating merge tree, and this defines the behavior of this table. And the primary key here is the bucket. And in an aggregating merge tree, the primary key not only defines the order that data lives on disk, it also defines how the rows get collapsed or aggregated. So in this case, if we have 2 records that have the same bucket, so the same minute in time, ClickHouse will collapse those and aggregate that data when it does its merging. Now to get data into this aggregate table, ClickHouse has a feature called materialized views. They're a little bit different to materialized views in other databases. These act like an insert trigger. So every time you insert into the source table, it automatically just inserts it into this other table. So we have our materialized view called requests XL by minute MV, which is the convention for materialized views. Our destination table is our aggregating merge tree table. And then we define the source of the data. So we're going to select they're going to take the timestamp and round it down to the start of the minute. We're going to count the number of requests coming in this particular insert, the minimum, the maximum, and then we want to calculate the average. But again, we're inserting into an aggregate table here, and because this is a more complicated aggregate function, we have to use this average state. And it tells it to store not only the average value, but enough state to be able to re-aggregate that later on. And so this is our source table, the request XL, our raw data, and then grouping by bucket because that is our primary key and that's how we want that data grouped together by minute. So the way data flows into the system, we have an insert statement where we're inserting our rows. Here we just have 2, but normally you might have 10,000, 100,000. The data goes into the source data table, so our request XL table as 2 individual rows. The materialized view kicks in because an insert has happened, and it inserts that into our aggregating merge tree table. And it'll only insert 1 row here because both of these were for the exact same minute in time, so it aggregates that data, inserts it into the table with a count of the 2 requests, the fastest, slowest, and average. Further inserts will insert into this table, and the merge process will collapse any that are for the same minute down into the 1 row for that minute. So let's query this aggregate table now. So we saw that it took about 1.3 seconds, I think, querying the raw data. So let's query the aggregate data. Now we are grouping by minute, but this query is grouping, we still want to get the daily stats, so it's going to combine all of those minutes for that day live into the result. So it still has to do some aggregation at runtime, in addition to the pre-aggregation that it's already done. So this query took 7.3 milliseconds, and this is 100 billion rows worth of data that has been processed. But we can see that because this is the aggregate table, it only had to read 44,640 rows to do this because that's actually the number of minutes in 31 days, which is the size of this data set. So this lets us basically have an unlimited amount of data that we can query because if we had 100 billion, 200 billion rows in that month's worth of data, this is going to be a maximum of 44,640 rows once it's all aggregated because it gets grouped by minute, and so we know this is always going to be fast. Now, you might be wondering, how do we handle updates in a data where the parts are immutable? We do have some use cases in Nightwatch where we do need to update data. So we track the users of your applications that are making the requests so that you can help your users if they're having problems. We don't want to capture the username, their full name and all that data on every single event because that's a lot of data when you're talking about billions and billions of rows. So on the individual event rows, we just want to store the unique identifier, and we want to store the user details in a separate table. Now, if the user changes their username or their name, we want to make sure we keep that record up to date. So we want to update that table as data's coming in. So let's have a look at a simplified version of our users table. So we just have 3 columns. We have the ID column. This is the unique identifier in your system. We have the username, and then we have the name. Now, Nightwatch lets you customize what data is actually captured here. So if you need to redact any of this information, you can. We're going to use a different engine here called the replacing merge tree. So this is an extension on the merge tree engine. And the cool trick about this one, when we define our primary key, which does define how the data is ordered on disk, but it also means that if there's 2 rows that have the same primary key, it will only keep the latest version of that data. And when we insert the data, we'll see that you can have multiple rows for that primary key, but at merge time, these will get collapsed down and down. So let's have a look at this in action. We're going to select star from our users table, and there's currently 0 rows in this table. We're now going to insert 2 users into here. So we've got user ID of 1, username Jess Archer, name Jessica Archer, and then we've got one for user ID 2, username Taylor Otwell, and full name Taylor Otwell. So we'll insert that into our replacing merge tree table, and now we're going to select star from that users table again, and nothing exciting here. We can see there's just the 2 rows we just inserted. So I put my name in here as Jessica Archer, but that's what my mum calls me when I'm in trouble. I want to change it to Jess Archer. That's what my friends call me. So instead of updating that row, I'm just going to insert a new row into that users table with the same ID of 1, the same username, but I'm going to set the name to Jess Archer this time. So we'll insert that data now, and now we're going to select star from this users table. And now we can see there's 3 rows in here. So we didn't actually update the data, we just inserted a new one, but we can see that there's 2 rows that have the same ID for me. So that's because the data has not been merged yet by ClickHouse. Merging happens at maximum once every 4 hours, but often much, much faster. So when we're querying some of these tables, if we're not using aggregate functions to query it, we can add this final keyword onto the end, and this tells ClickHouse to merge in memory the data for this query. So if I run this now, with final on the end, we only get our 2 rows, and we can see that the row that's been returned for me has my updated name on there. Another question we often get is how do we isolate tenants in our multi-tenant system, and how do we prevent noisy neighbors? So a noisy neighbor might be another customer of our system that has billions of rows coming in, and then there's your application there. How do we prevent all of their data from not slowing down your experience of the application? So if we have a look at our requests table again, where we had our timestamp, URL, status, and duration, well, in reality, we have an extra column on here, which is the environment ID. So in Nightwatch, every application can have multiple environments, and so the tenants in this table is each environment that we're tracking data for. And most importantly, the environment ID becomes the very first key in our primary key. So this means that all of the data for environment ID 1 will be ordered together, and then environment 2, and so on. And we can see what that looks like here, where all of this data for environment ID 1 is there, then it will order by timestamp, all of the rows for environment 2, and so on. And so when we query this data, we always filter by environment ID. We enforce that on our query builder, and it basically means ClickHouse is able to zoom in, and it's like those other rows don't even exist because of the way the index works. It can just scan to just your data and not have that noisy neighbor impact. Another question we get is how do we manage data retention? When we've got billions of rows coming into this database, we hold data for up to 90 days. How do we deal with cleaning that data up? Well, ClickHouse makes this really easy. So again, we have our request table here, and we have our timestamp column. So we can use this timestamp column and just tell ClickHouse using this TTL statement, or time to live, on the database structure. And in our case, we can say the TTL of every row that's inserted is the timestamp of that data plus an interval of 90 days. And ClickHouse will automatically take care of deleting that data for us. It doesn't delete it immediately on the 90-day mark. It deletes it at merge time. We can make this a little bit more performant if we want by petitioning the data. So we can petition by date, and it will effectively mean that when these parts get merged together, it won't create one massive part, it'll create 1 part per day. And we can use this to our advantage with this setting here called TTL only drop parts equals 1. And this tells ClickHouse, don't try and delete anything until you can delete an entire part. And that means that once all of the data in that part or in this day is no longer within the window, it can just delete that entire folder. It doesn't have to do anything within the files, it just deletes the entire thing, super fast, super efficient. Now you might be wondering, how do we detect exceptions that are occurring in your applications when we have billions of rows flying at us? I think we have about 17,000 per second on average at the moment this week. So how do we detect when an exception occurs in your application so that we can notify you? And how do we detect when an exception that you've marked as resolved happens again? So we recently changed the way we did this. The way we used to do this was every minute we would kick off a job for every single environment in the application, and we would run a query on our exceptions table for the last minute's worth of data to look for new exceptions. This was pretty inefficient, and it also meant that we weren't detecting exceptions as fast as I wanted to. So if the exception occurred 1 second after we had just checked, it could be just up to a minute before we then look again to find that exception. It also means there's a lot of environments in our system, if they're not having exceptions, we're still looking at them all the time saying, have you had an exception? Have you had an exception? And the more and more environments that were coming on, the harder and harder this got. This was the perfect thing to get us started, but as we grew, this became a problem. So we recently implemented an entirely new way of doing this using the power of ClickHouse. So if we have a look at our exceptions table, or a simplified version of the raw data where the exceptions are coming into, we've got our exceptions table, we have our environment ID for our tenancy, the timestamp of the exception, the class name of the exception, so whether it's a runtime exception or invalid argument exception, and then we have the message text for the exception. This is the merge tree engine because this is our raw data, and our primary key, again, is the environment ID first and then the timestamp. So we can create a aggregating merge tree table. We call this one pending exceptions, and this is where we can ask ClickHouse to keep track of just the count of how many exceptions have occurred. So we have our pending exceptions table that also stores the environment ID because we need to make sure that the data, a runtime exception in your application is different from a runtime exception in someone else's. We store the class of the exception, and then just the number of occurrences, so the sum of occurrences that have occurred of that exception, using the aggregating merge tree engine, and with our primary key of the environment ID, and this time the class. And because this is an aggregating merge tree, this means that if 2 rows have the same environment ID and class, again, ClickHouse will aggregate those together. So we need a materialized view to get the data into this pending exceptions table. So we have a pending exceptions materialized view. The destination is our pending exceptions aggregate table. And then we define the source of the data. So we're going to select the environment ID, the class, and the count of occurrences for every insert that comes in from our source table, our exceptions table, grouped by the environment ID and class. So let's have a look at this in action now so that we can really understand what's happening. So we're going to insert 2 new exceptions into our source data table here. We've got an exception for an environment ID 123 that's happened just now. It's a runtime exception with a message, and then an exception for a whole different environment, 456, also happens now, but is also a runtime exception. So we'll insert those 2 records, and now we're going to query for the pending exception. So we're just going to select the environment ID, the class, and the sum of occurrences from our aggregated table. And we can see that for environment 123, we had 1 occurrence of the runtime exception, and environment 456, also 1 occurrence of the runtime exception. So now let's insert another occurrence into here. So for environment 123, we're going to insert another occurrence of the runtime exception with a different message. We don't store the message in the aggregate table because it's not relevant for that. So we'll insert that row now, and so now we'll query our pending exceptions aggregate table. And now we can see that for environment 123, there's been 2 occurrences of the runtime exception. So what this means is, instead of waiting and querying once every minute, we can now query this table in an infinite loop and just check how many occurrences have happened for each environment, for each exception. But how do we acknowledge that we've received this exception, that we've checked whether it's a new one or whether it's an existing one that's reoccurred? So we can acknowledge these exceptions by inserting values directly into the aggregate table rather than the source table. So for environment ID 123, we're going to insert a negative value into that occurrences column. We had 2 occurrences of the runtime exception that we're acknowledging. We'll insert a -2, and for environment 456, we'll insert a -1. So we'll insert those 2 new rows in there, and we'll now query this table, and now we can see that there are 0 occurrences of the runtime exception in both environments. Now, while we were performing this in this endless loop, data's coming in all of the time, but because we're not setting a Boolean that we acknowledge the exception, we're just reducing the count by whatever we acknowledge. So if a new one has come in the meantime, in the next loop, we will see it again and check whether whether we need to do anything about it. Now, we've got these 0 rows in this table. We can use the TTL to actually delete these rows once they get to 0. So at any one time, this database tends to only have 100 or so rows in it that are constantly filling up and getting smashed down every second as we're checking this data. And this means now we detect exceptions as soon as they come into our system, and we can notify our users much quicker, but also much more performantly. We're now querying a very small table, and we're only querying for activity that has occurred. We're not checking tables to see if data was there for environments that haven't had any exceptions. We just ask this table and it tells us. So you might be wondering, how does ClickHouse work in Laravel? Well, it's pretty straightforward. There's a third-party package we use called PHP ClickHouse Laravel. It extends on a PHP SDK for ClickHouse, and this lets us use Laravel's query builder to query ClickHouse like we used to. So in our system, as I mentioned, we have Postgres tables for each region. We have ClickHouse databases for every region. So we can define that we want to talk specifically to our ClickHouse connection. And now ClickHouse has a lot of non-standard SQL functions. So most of our select statements, we use select raw because there's just a lot of things that the query builder doesn't know about that are very specific to ClickHouse. So our select statements are normally raw, but everything else is just standard query builder, where we can add our conditions, our group bys, and we can use the power of the query builder to conditionally add filters depending on what you're searching for. So it's a really nice experience to use this, and the Nightwatch dashboard is a Laravel app that just queries lots of different databases to present this information for you. So that's everything I have for you today. Make sure you check out Nightwatch if you haven't already, or come talk to us at the booths out the front.
How do you feel back in India?
So good to be back. I love India.
You love India?
I love India.
Then stay in India. Don't go back.
I love Australia as well.
Yeah. We can take her to mountains of Himalayas for bike riding.
Bike riding, mountain biking?
Yeah,
or motorbike riding?
The tallest peak of the earth is in India.
Oh, wow.
Yeah, where I have been there.
Yeah?
Yep. So for you, single piece of advice.
Okay.
So along with some of the questions, they are not just advice, but they are your opinions as well.
Okay.
So that's how we'll do rapid fire with you.
Okay.
So can we start? First question. One thing teams should start doing earlier to understand their system better is?
I would say instrumenting your system. So having these sensors in place that can tell you what is happening in your system, in your production environments. It's easy to see what's happening locally when there's only a little bit of data in there, but once it goes into production, it's kind of almost the Wild West when the users come in there and they're doing all sorts of stuff. So having that instrumentation, and that's what's great about Nightwatch, is you just install it and it instruments Laravel for you. It understands Laravel, it knows all of its events, so you don't have to configure anything, you just install it and it's instrumented out of the box.
Okay, second question. At scale, what usually causes more problems, code quality or decision making?
I would say probably more decision making. Code quality can be fixed. There are definitely cases where code quality can cause issues, but most of the time they can be resolved fairly quickly. Decision making tends to have longer term implications that are a little bit harder to kind of fix, but we don't always know at the time. There's a lot of things we kind of did up front that we thought like we just had to kind of make some assumptions. This is going to be the best thing. And we can always change those decisions later, but it is often harder to sometimes.
Yep, true. Thank you. Question 3. Working closely on Laravel's own products, what changed most in how you think about responsibility?
And that's a tough one, right? So I guess working on Laravel products means that we're creating tools that are not just used by my customers, but my customers. So it expands the reach of things. There's things that I can do that if I cause a problem, it can cause a problem for a lot more people. So we have a very high responsibility to maintain that high quality. A lot of people are using Laravel for medical systems, government, police, all these sorts of things that are really important. So we have a massive responsibility.
And you have seen, like, you were the earlier part of Laravel team and scaling to up, so
yes,
you've been part of the journey. Next question, 4. One simple practice that saves most of the time during debugging is?
I would say making sure that you've, again, got that instrumentation, but adding the extra context that you need. So adding logs when there's, especially things that kind of reach outside of your system, where it's much harder for you to control what's happening, so external services. So adding some logging in or using Laravel context to just capture those little extra bits of data that are custom to your application that will help you debug the problem when it occurs later. Because there's nothing worse than having a problem and then thinking, oh, I could solve this if I just had added this one little thing that told me this. So adding that ahead of time and kind of planning for that, I think is really key.
Thank you. Question number 5. When monitoring production system, what mistakes do experienced teams still make?
I mean, a lot of experienced teams aren't monitoring their production, at least not in enough detail. So I guess one mistake is just not doing it at all.
Yeah.
And
I feel that it's okay not to do it.
Yes, and just having the right notification set in place. You can install a system, but if you're not actually checking it or have notifications set up, then you may as well not have it in the first place. So being proactive, maintaining it and monitoring it, especially when you're making changes during deployments, all that time is especially sensitive, or during high activity periods, if you have a Black Friday sale or something. So yeah.
6th, one mindset that helps most when working with real world system is? Mindset. One mindset.
I think thinking more about the real world. So thinking more about realistic data scenarios. So not kind of foobar baz data, but actually trying to get real world data at least as close as possible. When we built Nightwatch, we very early on installed it on Laravel Forge so that we could work with real data and actually test our assumptions and validate that it was actually helping us solve problems. When we had our kind of fake staging data, we would imagine problems, create the data, and then it would tell us, yes, we found this problem, but it found the problem that we told it to find. We needed to make sure that it actually found the problems that were actually happening that we didn't even think of.
Yep. So being realistic is one of the mindset.
Yes.
Yep. 7th, one piece of advice you'll give teams working on a product used by thousands of people is? One piece of advice in one word.
My answers are too long. Quality.
Quality. Yeah, perfect. 8. See, it goes with the flow.
One word.
One piece of advice you'll give your younger self based on your experience is? One word or maybe one statement.
Put yourself out there and show up every day.
Yeah, so that's your younger one advice to yourself.
Yeah.
Okay, great. Number 9, coming from Australia, what perspective has it given to you in global tech?
There's so many different ways of working and cultures and all that sort of stuff. So I guess the perspective is to engage with other communities and other cultures and incorporate that. We're much stronger when we work together.
Yeah.
So yeah.
And being in all time zone.
And being in all time zones. Yeah, time zones are hard.
True. Last question. After experiencing Laracon India, one thing that stands out to you about community is?
The friendliness, the kindness, the caring. I love you all.
Wow, that's the ecosystem. All right, thank you, Jess. One question from audience, which will take it.
Okay.
Could you please let us know when what is the most difficult challenge that you faced while developing Nightwatch, and how did you tackle that issue?
It's really just the amount of data, the sheer volume of data. Like a DOS attack happens to one of our customers, that is more data. So your DOS attack becomes our DOS attack. Your Black Friday sale becomes our Black Friday sale.
Yeah.
So just dealing with that sheer amount of data, and that's what my talk with ClickHouse, all of that, just trying to deal with all of that data is, very big.
Perfect. Thank you, Jess. Thank you for being in India.
Thank
Thank you
much.
once again.